Before starting, put the auto-generated YouTube subtitles in French or your mother tongue to get everything, and slow down or speed up the pace as needed. If you don't have time to watch it, just listen this video as a podcast while doing something else. Now listen and learn English as exploring our world. What if the universe isn't what it seems? We picture space as vast and flat, but what if it can be bent or folded, bringing distant points close together? Like folding a map, the impossible distance could become a single step, a shortcut through the cosmos. This is the idea of a wormhole, a tunnel through space, blurring the line between science and imagination. The wormhole sits at a crossroads, where Einstein's equations meet the boundless creativity of science fiction. Born from general relativity, it's a real solution to the math, yet also a gateway for storytellers to imagine travel across galaxies. Scientists debate its reality, while fiction inspires us to dream. The wormhole bridges science and imagination, fueling our quest to explore the unknown. A wormhole, or Einstein-Rosen bridge, is a theoretical tunnel through space-time, a cosmic shortcut connecting distant points in the universe. Imagine marking two dots on a sheet of paper, then folding it so they touch. Suddenly, the distance vanishes. Wormholes could let us leap across the cosmos, redefining what's possible in space travel. It's a mind-bending idea that challenges everything we know about space and distance. A wormhole is a theoretical tunnel in space-time with two mouths and a connecting throat. Looking in, you'd see a distorted view of a distant place, like a cosmic window. To keep a wormhole open, physics demands exotic matter with negative energy, something never observed. Wormholes are possible in theory, but their stability remains one of science's greatest mysteries. Wormholes could connect distant stars, alternate universes, and even different times, turning science fiction into reality. Imagine traveling across the galaxy in minutes or glimpsing other realities. These cosmic shortcuts might even let us visit the past or future, though paradoxes could arise. Wormholes remain one of the most mind-bending ideas in physics. The story of the wormhole began not as a search for shortcuts, but as Einstein wrestled with troubling infinities in his theory of general relativity. Carl Schwarzschild's solution revealed black holes, singularities Einstein disliked. In 1935, with Nathan Rosen, Einstein tried to remove these singularities, seeking mathematical elegance. Their work led to a new idea, a smooth bridge in space-time, now known as the Einstein-Rosen bridge, a wormhole. In 1935, Einstein and Rosen described a bridge, now called the Einstein-Rosen bridge, that connected our universe to a parallel one. This theoretical wormhole was a smooth tunnel between two spacetimes, but it pinched off too quickly for anything to cross. They imagined particles like electrons as tiny bridges, but the idea was soon replaced by quantum mechanics. Decades later, physicists revived the concept, inspiring new ideas about wormholes and the universe. The Einstein-Rosen bridge began as a mathematical curiosity, dismissed as unrealistic and forgotten by most physicists. In the 1950s, John Archibald Wheeler reimagined it as the wormhole, a shortcut through spacetime. The name captured imaginations, inspiring science fiction and transforming the bridge into a cosmic icon. In 1935, Albert Einstein shook physics with two revolutionary papers. One, with Nathan Rosen, introduced the concept of wormholes. The other, with Rosen and Boris Podolsky, challenged quantum mechanics with the EPR paradox. These works question the very nature of reality, from the vastness of space-time to the mysteries of the quantum world. Decades later, their surprising connections still fascinate scientists today. Einstein's EPR paper introduced quantum entanglement, where two particles remain linked no matter how far apart. If one is measured, the other's state is instantly known, even across the galaxy. This spooky action at a distance troubled Einstein, as it seemed to defy relativity's speed limit. He believed hidden variables explained the connection, arguing quantum theory was incomplete. For years, the EPR paradox and Einstein-Rosen bridge seemed unrelated, one a quantum puzzle, the other a curiosity in relativity. But what if entangled particles aren't truly separated? Maybe on a deeper level, they're connected by a hidden bridge, a microscopic wormhole. This idea, ER equals EPR, suggests the universe is stitched together by quantum threads, hidden connections shaping reality itself. In 2013, the world of theoretical physics was shaken by a proposal that was as elegant as it was audacious. Physicists Leonard Susskind of Stanford University and Juan Maldacena of the Institute for Advanced Study, the very institution where Einstein had worked, put forth a stunning conjecture. They suggested a deep and fundamental connection between two of Einstein's most famous and seemingly unrelated ideas. This conjecture was captured in a simple, powerful equation: ER equals EPR. On the surface, it looks like a cryptic line of code, but its meaning carries the weight of a potential revolution in our understanding of the cosmos. It proposes a direct equivalence between two cornerstone concepts in modern physics. Let's break down this profound statement. The ER on the left side of the equation stands for the Einstein-Rosen bridge, the original name for a wormhole. This represents the world of general relativity, the theory of gravity, geometry, and the macroscopic structure of spacetime. It is the language we use to describe planets, stars, galaxies, and the very fabric of the universe. The EPR on the right side stands for the Einstein-Podolsky-Rosen paradox, which is a shorthand for the phenomenon of quantum entanglement. This represents the bizarre and counterintuitive world of quantum mechanics, the theory that governs the behavior of particles at the smallest possible scales. The equation ER equals EPR, therefore, makes an extraordinary claim. These two concepts are one and the same. It suggests that a wormhole, ER, is simply the geometric gravitational description of quantum entanglement, EPR, and conversely, quantum entanglement is the quantum mechanical description of a wormhole. According to this idea, whenever you have two particles that are entangled, they are physically connected by a microscopic Einstein-Rosen bridge. The spooky action at a distance that so troubled Einstein would be nothing more than a local connection through this hidden tunnel in spacetime. The two phenomena are not just related, they are two different languages describing the same underlying physical reality. This proposal is not just a clever analogy, it is a serious hypothesis rooted in the mathematics of string theory and quantum gravity. It provides a potential bridge between the two great pillars of modern physics, general relativity and quantum mechanics, which have famously resisted unification for nearly a century. If ER equals EPR holds true, it means that the geometry of spacetime is not separate from the quantum world, it is built from it. The very fabric of the universe might be woven from the threads of quantum entanglement, with every connection creating a tiny, imperceptible wormhole. It's a breathtaking idea that reframes our entire picture of reality. Imagine two black holes created from entangled particles. Though separated by vast distances, quantum mechanics says they're linked. The ER equals EPR conjecture proposes these black holes are connected by a non-traversable wormhole, a physical bridge, not just a spooky quantum link. This idea could help solve the black hole information paradox, suggesting information escapes through the wormhole to its entangled twin. The ER equals EPR hypothesis really elevates the relationship between geometry and quantum information to a whole new level. It suggests that spacetime itself isn't actually a fundamental entity, but rather, it's an emergent property. In this view, the smooth, continuous fabric of the universe that Einstein's general relativity describes is actually constructed from a discrete quantum foundation. The building blocks of this foundation are qubits, the basic units of quantum information, and the force holding them together is entanglement. The more entangled a set of qubits becomes, the more tangible and classical the geometry of the spacetime they create. It's almost as if the universe is a giant quantum computer, and spacetime is its operating system. This perspective totally flips our traditional understanding of cause and effect in physics. We used to think of spacetime as a pre-existing stage where the drama of quantum mechanics unfolds. Particles move through space, and their separation is defined by the geometry of that space. But ER equals EPR suggests the opposite is true. It's the quantum entanglement between particles that actually creates the geometry in the first place. The distance between 2 points in space might simply be a measure of how little entanglement exists between them. Maximum entanglement would mean the points are connected by a wormhole, effectively making the distance between them zero. This idea has led to a pretty powerful new principle in physics known as it from qubit. It's the notion that everything we see in the physical universe, matter, energy, gravity, and the very geometry of space and time, emerges from the underlying reality of quantum information. Spacetime is like a hologram, a three-dimensional projection generated from a two-dimensional surface encoded with quantum data. The wormholes of ER equals EPR are a key part of this holographic picture, acting as the threads that stitch the hologram together. They're the physical manifestation of the quantum code that writes the laws of the cosmos, connecting distant bits of information. And while ER equals EPR is still a conjecture and not a proven theory, it represents one of the most exciting and fruitful avenues of research in fundamental physics today. It provides a sort of dictionary to translate between the language of gravity and the language of quantum mechanics, allowing physicists to use tools from one field to solve problems in the other. It suggests that the universe's greatest mysteries, the nature of black holes, the origin of spacetime, and the spooky connection of entanglement, aren't actually separate puzzles. Instead, they're all different facets of a single unified reality, where geometry and quantum information are truly two sides of the same cosmic coin. The dream of stepping into a portal and emerging light years away is thrilling, but wormholes are unstable, violent, and tiny, collapsing before anything can pass through. Even if we could find one, it would be microscopic, far too small for travel. Overcoming collapse, size, and deadly radiation makes wormhole travel the ultimate cosmic obstacle course. To keep a wormhole open, we'd need something extraordinary. Exotic matter with negative energy density. Unlike antimatter, exotic matter would repel gravity. Imagine a ball that falls up. This repulsive force could prop open a wormhole, but we've only seen tiny hints of negative energy and quantum effects like the Casimir effect. The amounts are minuscule, nowhere near enough to stabilize a wormhole. Creating or finding exotic matter in bulk would require a revolution in physics. Until then, traversable wormholes remain pure theory. Most physicists agree, traversable wormholes are probably impossible with our current knowledge. The obstacles, instability, radiation, and the need for exotic matter, are immense. Yet history shows science can overturn the impossible. Unifying relativity and quantum mechanics might reveal new possibilities. Even if wormholes remain fiction, studying them pushes the boundaries of our understanding. The journey to the stars may start not with a spaceship, but with a single, world-changing equation. Black holes and wormholes both warp space-time, but they're fundamentally different. A black hole is a one-way trip. Nothing escapes its event horizon. A wormhole, if stable, is a two-way tunnel, a shortcut, not a prison. Some theories link wormholes to white holes, the hypothetical opposites of black holes, but white holes likely don't exist. The confusion comes because a wormhole's mouth might look like a black hole. The key difference: black holes trap, wormholes connect. One is a cosmic dead end, the other a potential bridge. Wormholes could, in theory, allow time travel thanks to relativity's time dilation. Move one mouth at near light speed, bring it back, and the two ends become desynchronized in time. Step through, and you could emerge years in the past. This creates paradoxes, like the grandfather paradox, that trouble physicists. Some, like Hawking, suspect unknown laws would prevent such time machines. But if stable wormholes exist, time travel might be unavoidable. Wormholes aren't just cosmic shortcuts, they're the ultimate paradox. Wormholes are a storyteller's dream, solving the problem of vast cosmic distances. They let heroes cross galaxies in moments, as seen in and even superhero tales use wormhole-like portals for instant travel. Their roots in real physics give stories credibility and depth. Fiction, in turn, inspires real scientific curiosity and wonder. Wormholes bridge science and imagination, inviting us to dream bigger. They're not just plot devices, they're gateways to possibility. Science fiction mirrors our hopes and anxieties about discovery, using wormholes as symbols of exploration and the unknown. These journeys reflect the spirit of science, a leap into the unknown, driven by curiosity and the quest for understanding. Ultimately, wormholes in fiction remind us how much we have yet to learn, and inspire us to keep exploring the boundaries of knowledge. The Einstein-Rosen bridge is more than a tunnel through space-time, it's a symbol of human curiosity. It bridges not just space but the worlds of science and imagination. The wormhole stands as a beautiful symbol of our quest to understand everything, a bridge built of pure curiosity. Our journey through wormholes is just the beginning. The ER=EPR conjecture hints that reality is woven from quantum entanglement, and physicists are exploring these mysteries today. The quest to understand the universe continues, with new theories and discoveries always on the horizon. Join us next time as we explore even deeper questions, because the cosmos awaits.